All right, so today I'm going to introduce you, well, not introduce you because we've already been using limits so far, but what we've used in the Newton quotient is like a special type of limit. It was the limit as this h value approaches 0, so we were talking about like the interval between the x's and how it gets closer and closer and closer together. But I can calculate a limit for any function. Basically, the limit is some point that we're looking at, so we call that maybe like point A. In the domain of the function. And if I want to find the limit as we approach that particular x value, I'm trying to figure out what that function approaches as its argument, so we use the word argument, approaches a. So we'll touch on what is an argument in a second. This is kind of the idea of calculus, like we can't do the Newton quotient without the idea of a limit, so approaching some particular value, right? But we can also do it just to kind of see what a function is approaching. So the argument of a function is a specific input, and it's also known as the independent variable. So usually when we look at a function, the argument of the function is the x value. So what does this kind of say in regular language? I want to know what the function approaches, or what the y value approaches, as the argument or the x value approaches a particular number or value in the actual domain of that function. Okay, so there's a couple ways that we can find limits. If I'm given a graph, I should be able to find a limit. I can also do it with equations. So let's take a look at a couple graphs here, or just one graph, a couple of scenarios. Okay, so this is telling us that we want to know what the limit is as x approaches 1 of f at x. So this graph right here, both parts of this are the graph of f at x. This is kind of like one of those piecewise functions that we talked about earlier in this unit. So as x approaches 1, what is the y value that's being approached? That's kind of the question that we're being asked. So if we take a look at this, if we approach the x value 1 from either side, what are our y values getting closer and closer and closer to? 0. So the limit as x approaches 1 of f at x is 0. Okay, so sometimes it will literally be what f at 1 is equal to. All right. Let's take a look at the next one. The limit as x approaches negative 2 of f at x. So here's negative 2. 3. Yeah, I'm approaching the value 3 as we approach from the left and the right. Awesome. Okay, now we're running into something a little bit different. I have the limit as x approaches 0, and I have this little thing that looks like an exponent, which is a plus. And what this means is from the right. Okay, so this is asking me what is the limit, or what are the y values approaching as x approaches 0 from the right. So here's 0 right here. And as I come toward it from the right, what are my x values approaching? Or sorry, what are my y values approaching? Negative 0.5, right. Is that the same from the left? If I were to approach an x value of 0 from the left, am I also approaching negative 0.5? Yeah? Yeah, for this case I am. But for some cases it's going to be different. I may not always be approaching the same value from the left that I am from the right. So just such a scenario is actually next. So here I'm interested in what the function is approaching as x approaches negative 1, and you'll see this little negative exponent. Kind of looks like a negative exponent. If the plus exponent means from the right, this one of course means from the left, yeah. Okay, so I'm going to start at the left, and I'm going to trace along my function, and as I get closer to negative 1, what are my y values approaching? I heard it somewhere. 2, yeah. Great. Now this guy's from the right. So if I approach negative 1 from the right, what are my y values approaching? Yeah, so the limit as we approach -1 from the right is actually -1. Although the function actually is undefined there, but we're still approaching that value, right? Okay, so what is the limit as x approaches -1? If I approach something from the right and something from the left, and they're two different things, what do we choose? Why 2? So you're saying it's defined here, so we should choose that one? Liam, what do you think?
Yeah, I was thinking it's like it's a hollow point on the lower one, and it's like actually defined on the top one, so you choose that one.
Okay.
The y2 minus y1?
Oh, so you're saying we should take the difference of these, maybe? I kind of asked you a trick question. I did. The limit here actually does not exist. And with that, now we know why in Mean Girls she says the limit does not exist. So you're welcome, everybody. Just made your week right there. Exactly, yes. Okay. Pardon?
It was actually on
What? Yeah, it was, yeah. Remember she was on like the mathletes team?
Oh.
Okay, so we will say DNE for this one does not exist. Here's the big thing. If my limit from the left is not the same as my limit from the right, automatically that limit cannot exist. If I'm approaching two different things, I'm not approaching one single thing from the left and the right, so I can't have a limit that is approaching one particular value. The limit has to approach one particular value. So left and right limits must be equal for the limit to exist. Okay, so that's kind of formalized here for you in the conditions for a limit to exist little box that we have down here. So the limit as x approaches some value a in its domain of the function f at x exists if three criteria are met. The right limit must exist, the left limit must also exist, and the left limit must equal the right limit for that whole limit to exist. So that's the deal. Three things that need to be present. Can I scroll?
So does the line end? Like if you have a line that just ends somewhere and it says like approaching from the left, if there's no line outside.
So in order for us to calculate a limit, it must be as x approaches like a particular value that's actually in the domain of that function. So if a line ends, I can't choose any x values that are off of that graph, right? So it has to be a value in the domain itself. Good question. Okay. So there's graphs for you. We can also evaluate limits of functions. So when we evaluate limits of functions, we are always going to try substitution first. Okay, so you guys know when we were doing our Newton quotient, we had the limit as h approaches 0, and eventually in our Newton quotient calculations, we actually subbed in 0 for h, right? We tried, but earlier, if we would have tried that before, maybe common factoring out an h and canceling, we would have got that indeterminate form. So you want to watch out for indeterminate form or an undefined value. Like if I have 4 over 0, we know that that value would be undefined. So I might need to do some work with the functions first in order to figure out the limit. Okay, so we're going to try this one out. Once you sub in, you can drop the limit notation. If it doesn't work, then you need to go back and try something else. But we're going to first try with substitution here, see if we can calculate the limit as x approaches -1. And it gives us 4. Yep, thanks. Okay, is this an acceptable answer, -4? Is that okay? Yeah, that's fine. So substitution in this case works all right for us. Okay, let's try it out for the next one. See what happens if we sub in. So as soon as I sub in, I get to drop that limit notation. Sorry?
Well, we always have to try it first, or will there be like a method to know substitution?
Yeah, you kind of just have to try it. It's just a quick like plug in and calculate kind of deal. Alex?
How would we know that like the number is like reasonable, -1?
I mean, any number that is a real number is a reasonable number. 4 over 0, that's not a reasonable number, that's undefined.
Okay,
Or 0 over 0, that's indeterminate form.
okay.
Yeah. So in this case, we get 4 over 1, and our limit equals 4. Acceptable, that's a defined, it's a real number, so we're good.
Where do you get 0? Oh, x equals 0.
X is approaching 0, yeah.
Great.
So far so good? Not too bad?
Except for C.
Okay, so what's the problem with C, Jonathan?
Well, you see, infinity is incalculable, I think.
Yes, you are right. So that begs the question, how do I find the limit as x is approaching an infinite number?
There is no limit.
Jeremy says potentially maybe our limit could not exist. We're going to do a couple little tests here. Okay, I'm going to choose a big number. Let's say maybe we choose,
You can never reach infinity.
I know, we can't. So I'm going to choose bigger and bigger numbers here. So let's just start, maybe we can start with 100,000, 5 zeros. So I want to know when I put in 100,000 here, what we'll get.
Something that's not close to infinity.
Okay, so let's plug this into our calculator. What do we get here? Give me a good number of decimals. Alexandra, what'd you get?
1.50000325.
Okay, awesome. Okay,
There's 3 zeros.
oh, thank you. Okay, let's try 1 million. 6 zeros this time. Oh, that's 2.
Always throw extra zero in there for computers.
You can if you want. Who's got their calculators out today? I don't see a lot of calculating happening. Okay, what do we get?
1.5000325.
0, 0, 0, 0, 325. Okay, so we can probably guess what happens when we do like 1 billion, right?
Let me guess, 1.5000325.
1 billion? 9 zeros? Okay, let's calculate it. Yeah?
Is it 1.5? Is it 1.5?
The limit is 1.5. Yep, you're right. What do we get for this calculation here?
1.500000000.
Okay, there's lots of zeros, right? And then eventually it's 325. So Liam's got it. As we get closer to bigger and bigger and bigger numbers, the amount of zeros here is just going to keep getting bigger and bigger and bigger. So we're approaching, I think it's safe to say that we're approaching the value 1.5. Now, how could I have gotten 1.5 from this equation without having to do all of those tests?
So 5 and 4, so.
The Newton thing? What?
No, Newton is for slope of the tangent. That's for instantaneous rate of change. We're just trying to figure out what y value is being approached when the x approaches infinity. Easier than that. 3 divided by 2. Hey, look at that. This value right here, this is actually the horizontal asymptote of the function, 1.5. So we have a function that kind of looks like this. It's like when I have a linear function divided by a linear function, it's one of those functions that has the two pieces that we've talked about, hyperbolic functions. And it has a horizontal asymptote at 1.5. And I'm not sure exactly where this function, like if it curves like this or opposite. You could probably figure that out pretty quickly. But for our time's sake here, we have some kind of function that is approaching the asymptotes as it approaches positive and negative infinity for x. So as x approaches like positive infinity, let's say, my function is getting closer and closer and closer to 1.5, the horizontal asymptote. And if it approaches negative infinity, my function is also approaching the asymptote, right? No matter which way I'm going, I'm getting closer and closer and closer to that asymptote. So that's why it ends up being 1.5 for this one. Sorry, question? So this is only if x is approaching infinity or negative infinity, right? Because we're approaching, like we're going this way forever, and we're going this way forever. So we're getting closer and closer to that asymptote value. If it's just approaching a number, then we don't really use this in the same way. Okay? All right. Let's try substitution here. So if we do 3 squared minus 2 times 3 minus 3 over 3 minus 3, looks like we're getting 0 over 0. This is not an acceptable form. This is what we called that indeterminate form. I don't think I'll be able to fit that there. That means we probably have to do something else other than subbing in first. So because I can't sub in, I'm going to keep writing the limit notation. Any ideas as to maybe what we can do to simplify this equation or work with it in a bit of a different way? What do you mean by solve the top? Factor? Okay, what two things multiply to negative 3 and add to negative 2? Okay, so x minus 3, x plus 1. And that's great because now we can cancel out the x plus 3's. And we just have the limit as x approaches 3 of x plus 1 now. So let's sub in and drop the limit notation. X plus 3, or x minus 3 and x minus 3. Perfect. So now we have the limit is approaching 4. Okay, part of this is important to note that we actually are approaching an undefined point. Okay, that's why we get indeterminate form, is because I'm actually approaching a value that we know we can't enter into the denominator because it causes our denominator to be 0, right? So we know that that x approaching 3 value, if I were to actually calculate the point, it's an undefined point, right? It gets canceled out along the way. We talked about that at the beginning of our rational equations lesson 1. But I can still figure out what it's getting closer and closer and closer to, right? I can still figure out what it's approaching even though that particular point when x equals 3 is undefined. So that's why we end up getting 4 here. Okay. And then for our last example, it's important for us to understand as well that some limits can tend toward unbounded values. So they can tend toward negative infinity or positive infinity, right? Like if I'm looking at a function and it's going up or down forever, that's going up toward positive infinity or down toward negative infinity for y. And those y's wouldn't be approaching any particular value as I approach a vertical asymptote or something like that. So I can actually kind of predict what some values are going to do because I can kind of see here that we have x minus 1 in the denominator. What's the restriction when I have x plus 3 over x minus 1? What can x not be here? 1. But this is actually asking me to calculate the limit as x approaches 1 from the left. So I know that I'm approaching a vertical asymptote. The question is, am I approaching it from the side that goes up toward positive infinity, or am I approaching it from the side that goes down toward negative infinity? So if we try substitution here, we're going to get 4 over 0, right? If I just plug in 1 into the top and into the bottom. And this is going to apply that the limit tends toward either a positive infinity or a negative infinity. And it also should imply to us that the limit in some sense does not exist, right? And the graph has a vertical asymptote at this point. Okay, this is actually different than what we calculated above because in this case we just got indeterminate form. And I wasn't approaching an asymptote, I was approaching an undefined point. So in this scenario, when x equals 3, this is actually an undefined point because it gets canceled out along the way, which means that even though that point in particular is undefined, my y values are still actually approaching a particular value. Whereas when I have a vertical asymptote, my ends are shooting up and they're shooting down at either side of that asymptote. When I get number over 0, that should tell me that we're approaching a vertical asymptote. So my limit can't exist, but sometimes we still will tell whether it's approaching positive infinity or negative infinity. But if it doesn't actually approach a particular number, infinity, as we know, is just a concept. In that case, the limit doesn't actually exist, right? It's not approaching something in particular. So what we can do is kind of what we did above with that horizontal asymptote question. We could try a couple x's that are getting closer and closer and closer to 1 from the left. So if I think about a number line, right, here's 1. To the left of 1 is 0. So maybe that's the first thing I try in here, 0. And then maybe we get a little bit closer. We'll do 1.5 or 0.5. And then maybe I'll get even a little bit closer than that. Maybe I'll do 0.9. Right? And then maybe we'll try to get super, super close to 1. And then maybe we'll try 5 nines. And we're just going to keep getting closer and closer to 1 from the left. So if we try out 0, we're going to get 3 over negative 1. That's going to give us negative 3. Okay, if we sub in 0.5 here, I'm going to get 3.5 over negative 0.5. And that will give us negative 7. Okay, subbing in 0.9, we'll get 3.9 divided by negative 0.1 gives us negative 39. Okay, negative 0.999 gives us 3.999 over negative 0.001. That gives us negative 3,999. Okay, and then similarly, if we plug in with 5 nines,
It's negative 3,000, negative 300,009. Sorry, negative 399,999.
great. Okay, so I think we can kind of see what's happening here. As I get closer and closer and closer to 1 from the left, what are we approaching here? This is negative 309.
Like it just, like
Negative.
Negative infinity.
Negative infinity, yes, because this is just going to keep getting bigger and bigger and bigger and bigger. Yeah, so we would say that the limit as x approaches 1 from the left approaches negative infinity. Technically, an acceptable answer for this is also that this limit does not exist. Because I can't actually approach negative infinity, right? We know it's going down toward negative infinity, but can I approach a concept that keeps going on and on and on forever? No, not really.
Well, you'll accept it.
Yeah. Okay, so when you see something like this and you try subbing in and you get number over 0, this should tell you that you're approaching a vertical asymptote, and either you're going up toward positive infinity when you approach that or down toward negative. Especially when you have this like linear over linear function, they're pretty straightforward with that. Okay, any questions on limits? Oh, sorry, I forgot that I added this. Okay, so you guys will also see in some of your work that it's going to ask you to determine the limit of a sequence of numbers, so just like a particular set of numbers that goes on and on. So this guy, is this approaching any particular value?
Infinity.
Jonathan says infinity. Do you guys agree?
Yeah.
Well, what's going to happen after it hits 1 though? If I have 0.7, 0.8, 0.9, 1. Yeah, so this is just going to keep going forever and ever and ever, right? So Jonathan actually is correct. This is approaching, the limit of the sequence is approaching infinity. Or the limit does not exist in this case, right? Because it's not actually approaching any particular value. Okay, what about part B? Is this approaching any particular value?
Just going up and down.
Liam?
With like 0.09 bar notation.
But I'm also hopping back and forth between that and 1.
So we'll
But it's not going close to it.
Jonathan, what do you think?
Limit doesn't exist.
Payak, what do you think? You're right. This one approaches 1.
Oh, now I get it. Yeah.
Okay, because I'm getting infinitely close to 1, right? Even if I hop back and forth between that, the next one is going to be 99999, and then it's going to go to 1, and then 0.99999, right? So each of these is getting that much closer to the value 1 every single time we flip back and forth between those. So we're not saying it's equal to this. It's never in between the ones, it's never going to be exactly equal to 1, but it's getting super close to that, right? That's kind of what we're looking for. What is it approaching?
This next one is 0.
Okay, Jeremy says the next one's 0. What do you guys think?
negative infinity.
Negative infinity.
Is it number C? I said 0 because.
Oh wait, are you talking about the next one?
See, yeah.
Fraction keeps having it will never actually reach 0, but it will constantly keep worsening.
That's right. So we're getting smaller and smaller and smaller decimals, and those decimals are going to get infinitely close to 0. They'll never reach 0, but yes, this one approaches 0. Good job. Jonathan, is that what you're going to say as well?
I was going to say, yeah, there's an asymptote of 0.
Yeah, that's right. Awesome. Okay, so we talked kind of back in grade 11 about continuous and discontinuous functions, or maybe some of you did. Can somebody tell me what it means for a function to be continuous?
It continues.
Like it has arrows on the end?
Sure.
Lines go far.
The lines go far. Okay, if I draw you two pictures, maybe you guys can tell me which one is continuous and which one is not.
Oh, no. Yes.
So which one's continuous and which one is not continuous? The blue is continuous. Yes, that's right. Why is the blue one continuous and the red one is not?
No break.
Liam?
There's no break.
Okay, so I need to be able to trace my pencil from the left side of the graph all the way to the right side of the graph without lifting my pencil, right? That's the deal with continuity. So these conditions here, you're going to be asked some questions about whether your function is continuous at a particular x value. So whether it's defined at all x values, at the x value it's asking you about. And here's, or I guess not necessarily whether it's defined or not, but whether we have a gap in the graph at that point. So here's the deal. For something to be continuous at a particular point, so we're only talking about one single x value that it's continuous at. We're not talking about the whole graph. But for it to be continuous at that particular x value that you're being asked about, f at that x value needs to be defined, right? So it can't be an undefined value for your function. The limit as x approaches that particular x value needs to exist. When do I know if a limit exists? What's the conditions that need to be met for a limit to exist? Left and right limits exist and are equal, right? Okay, and the third condition is that our limit value, so if I decide the limit exists and I get the value of what the limit is, it must also be equal to the function at that value, okay? So when I figure out this, number 2, that it exists and what it's equal to, and when I figure out what f at a is equal to, if those are equal to two different things, then the third condition is not met here, okay? So I'm going to give you guys a couple scenarios here. I want you to tell me what you know about the limit, and I want you to tell me what you know about the continuity at that point A. Okay, so the limit as x approaches 2 from the right is equal to 3. The limit as x approaches 2 from the left of f at x is equal to 3. And f at 2 is defined, and it's equal to 4. So what do you guys know about the limit as x approaches 2? Let's start with that, of f at x. Does this exist? What is it equal to?
3.
Okay, so it exists and it's equal to 3. Condition 2 is met. It exists. Perfect. Is f at 2 defined?
Yeah.
If it equals 4, it's defined, right? That's acceptable. Okay, so condition 1 is met. Is the limit as x approaches 2 of f at x equal to f at 2? That is the question. Is this true?
Is 3 equal to?
It does not.
F at 2. Well, what's f at 2? What does the question tell us?
4.
So is f at 2 equal to 3? So these things are not equal, right? So condition 3 is not met. So the limit exists, but the function is discontinuous. Oops. Okay. Any questions on this one so far? Okay, what about part B? What do we know about the limit as x approaches 1 of f at x? Jonathan?
The limit doesn't exist.
Okay, these right limits and left limits are not equal, okay? That means that the limit can't exist here. So the limit as x approaches 1 of f at x, we would say this does not exist. And immediately, once I have this, I don't really care about anything else. The function is discontinuous. If the limit doesn't exist when x approaches 1, the function is immediately discontinuous at that point. So therefore, we can say the limit does not exist when x approaches 1 because the left and right limits are not equal. And therefore, the function is also discontinuous x equals 1. So as soon as the limit doesn't exist, the function's discontinuous as well. Just at that point, though. Okay, and I should probably note a, b, and c are different f at x's, different functions that we're talking about. Because, or I guess it could be the same function technically, but. Okay, the limit as x approaches negative 1. What can you guys tell me about the limit as x approaches negative 1 of f at x? Jeremy? Does it exist? Liam, yeah? What does it equal to? It equals 10. The left and right limits are equal, and they equal 10, so the limit must be 10. What can you tell me about continuity when x equals negative 1? Pardon? Why is it continuous, 5?
When you plug in x equals -1, the equation is still 10.
Okay, so the limit when x approaches negative 1 and f at negative 1 are both equal to 10, right? So therefore the limit exists, and the function is also continuous at this point. Perfect. The little tip off here is that we have 10, 10, 10. Okay, all of these things need to be equal for the function to be continuous. If you just have the left and right are equal, like in part A, we have the left and right are equal, but this one's not equal to 3. The limit exists, but it can't be continuous, right? Any questions? All right.